Okay, thank you everybody for hanging in. I am but a poor substitute for Jacob, but he's been working under my very loose supervision and has some interesting results that you'll see here today. It's a two-part talk. We're going to look at some relatively old zircons, xenocrystic zircons, in the far north, and you'll get an update on the craton scale isotopic mapping. Okay. You've all seen several versions of this slide, but what I want to emphasize here is that Mike Hamilton, Sandra Camel, and so on helped enormously with this by virtue of being superb archivists of zircons from past dating projects. And I don't need to say too much of anything about the Canada First Research Excellence Fund, but they're funding almost everything. Okay, now get this thing to behave. Oh, behave yourself. There we go. Hudson Bay terrain sits up here and can be followed around Hudson Bay up to the infamous Nouveau-Agatuk greenstone belt. The area that is of concern to us is this area B. It's just inside the Ontario-Manitoba border. Represents material that Denver Stone mapped back in the Dark Ages. When I go over to the right-hand panel, you can see in here we're really dealing with gneissic granodiorite, and the sample was right there. That sample, when it was subjected to Tim's work, Denver saw a 2740 age for metamorphic grains, and the igneous zircons yielded ages of 2850 and 3300. And I think it's that 3300 that attracted Jacob's attention. In fact, I know it was. So on my left, which would be your left, yes, you can see a Concordia diagram, and there's the Concordia curve, and the individual ellipses represent uranium, lead, and lutetium hafnium determinations, and the ones with little red cores represent additional trace element work on zircon grains. So when we look at this, we can see that there is a grain that lies in the 4.0 to 3.9 range, and more conventionally it's probably 3990 to 4.0. When we move over to the right-hand panel, we can see this is a plot of thorium over uranium versus age. And when we look at the old grains, we can see a couple of things. We can see the fact that there's a split on this diagram between igneous grains above the red line, metamorphic grains below the red line, and when we look at things over here at the 3.9 to 4 billion range, we're looking at igneous material. And yes, it's doing the right thing here. And down here you can see fully recrystallized cores without primary igneous zonation. Okay, here we can see on this plot epsilon hafnium versus age. So what are we dealing with? When we look at this group of samples in here, they are following this hafnium-defined trend that represents continuous reworking of Hadean-aged mafic crust. And that includes that stuff that's in the 3.9 to 4 billion range, and looking at it in terms of epsilon hafnium, or looking at it in terms of model age, there was a mantle separation age of about 4.15. When we look at this group up around 3.3, they are both chondritic down here, suprachondritic up here, and represent a juvenile event. When we look at this bunch in here at 2.85, find my place in the notes, we're talking in terms of, again, reworking of felsic crust. And what we see when we look at things in general is this. When we look at individual grains, we can see zonation in those individual grains that reflects the various igneous and metamorphic events. So it's quite unlikely that these grains represent detrital zircons. So you can cast that out of your mind. And when you look at the zircon grains in here, these are 3.99 to 3.97. The igneous zonation is preserved. Whereas when you go over here, you're looking at fully recrystallized cores. So what can we say? We're looking at magmatic reworking of Hadean crustal material during the Eoarchean. The circa 3.9 recrystallized zircon cores reflect the earliest recorded metamorphic event, full stop, on Earth. Second, this isn't on the slide. I got a phone call from Jacob on Tuesday morning, and that's the first time in 2.5 years he's actually phoned me. He found a second 4 billion year old grain in the southern complex down in Michigan. So stay tuned. Interesting things are about to happen. So on the isotopic mapping front, Jacob is dealing with gaps in the isotopic maps that you'll see later. He's got to include Christine Niemohen's data set, amongst others. In total, there are about 350 samples that contribute to the isotopic map that you'll see in a couple of minutes. So there is the distribution of uranium, lead, zircon ages contributing to the isotopic map. This is Ring of Fire. This is Denver Stone's work for the OGS. And, you know, we can come over here and look at the Abitibi and see more zircons than you really need. But you need them for purposes of work on mineral deposits and detailed work on stratigraphy. We would not have been able to do the Abitibi stratigraphy without the high precision that we get out of Mike Hamilton's work. So here is a simple age map. We can see the juvenile character of the Abitibi and of parts of the Wawa. And we can see relatively young material in the southern part of the Uchi domain. And something funny going on down here at Shibandwan. And we're not entirely sure what that's all about. And when you convert things to epsilon hafnium, those same features are pretty much present. We can see the Abitibi, we can see the Shibandwan area, etc. So Mike Hamilton's lab does excellent world-class work. We take it a tiny incremental step further by looking at xenocrystic grains that he says won't contribute to a good age. And indeed they won't, but there is information to be extracted from them. And the Abitibi and the Western Wabigoon are definitely distinct from the North Caribou terrain, geochemically, geophysically, and isotopically. The isotopic data indicates that distinct metallogenic terrains exist apart from the Abitibi. And that, for example, the North Caribou has distinct metallogenic styles. It shouldn't have a VMS at Confederation Lake, but it does. And that's as much as I have. Thank you for your attention.